In this lecture, I will talk about logistic regression. So this is our course, Machine Learning for Cybersecurity, right? And this is, the video in the sequence. We are using logistic regression in Tensorflow, right? And so currently we have covered, what is deep learning, what is TensorFlow. We started out, we saw that our transition was going to be to understand how to write algorithms. We would start with linear regression, right? And then from linear regression, we were going to go to logistic regression, all right? So we've already covered, this is linear regression, okay? And that we've covered already. Now the next topic is logistic regression, which is the one that we are covering today. And then after that, we will be able to move to neural networks. Very exciting, right? So neural networks of just, are defined as just having one layer, basically. So that will be the next one. And then finally, deep neural networks. And we will see that that's actually pretty straightforward to do once we've understood these two, linear regression and logistic regression. So we've actually spent a lot of time here, but it's actually very useful because it allows us to understand really well how everything works. We should spend less time here because we will already have the building blocks from when we did all of this. All right, so this is our video lecture for logistic regression in TensorFlow. So the learning outcomes of this, students will have a better understanding of logistic regression. So I will cover some of the theory of logistic regression. All right, so remember the focus of this is not the math. So focus is not the math per se, the math derivations or anything like that, the proofs, but instead we want to focus on the intuition. All right, and we will use the code to help us, but I will provide an example of a little bit of the intuition of this. And then after that, of course, is just we are learning how to use TensorFlow. TensorFlow. And in particular, how to code in TensorFlow. We've talked about computational graphs. And so the computational graphs that we're building are building themselves networks, right? So we want to learn how to build networks. So far, all we have done is we have built a very, very simple network that has two layers, an input layer and an output layer, right? And actually it turned out that our input layer only had one neuron and our output layer only had one neuron. So we weren't predicting classes, we were predicting numbers, real value numbers. So this was linear regression, all right, where we had one input x1, which was the square footage, and the output was y, which was the price. And the model had to learn the W for this, and then plus the bias, right? So that was our very simple network that we built. Now we are going to move to a slightly more complex network. This network will have, whereas our previous one had 1 and 2, this logistic regression model will now have, let's say, one more neuron at least, all right? And to keep it a little bit more interesting, we can add one more input or more. And so keep in mind that whereas before we had this, now we have something like that, a fully connected network. All right, every neuron is connected to all the neurons of the previous layer. All right, so that's where we're going now, but it's still pretty much the same, x1, so now it's x2. Now there would be a y1 and a y2, and notice how by just doing that, how many weights we've created. So we got 4 weights now instead of just the original 1, right? And you can imagine as you keep adding neurons to your problem, the number of weights is kind of growing like almost exponentially. So it becomes a more computationally intensive problem, and that's why at some point, we can't use CPUs anymore, and you have to start using other solutions like GPUs. But that's what's so great about TensorFlow is you can use that, and both of these solve our problem. So the term here is logistic regression, basically, all right, and TensorFlow. Okay. So let's go over a little bit of the information. So as I've said, kind of this is intuition, all right, and in particular, making that transition. We actually had a video where I showed a lot of the functions, etc., to make that transition from linear regression to logistic regression. And now, we're looking specifically at logistic regression with the goal of doing neural networks. So before we look at deep neural nets, as I've said, it's a good idea to look at logistic regression. Logistic regression is still a linear classifier, all right? So it still means that whenever you have data that looks like this, we can only build functions that look like that. So that's a linear function. All right, when we start doing neural nets, that's going to look a little bit different. We'll have possibly things like this. All right, and so in theory, we can start building other kinds of lines that are more curvy. All right, more curvy or other shapes. So logistic regression is still a linear classifier, but deep neural nets can be built on the ideas of logistic regression. It turns out that whereas, with logistic regression that looks like that, we can only build things that look like that. But with neural nets, we have now several things. We have hidden layers, right? And we also have functions that modify the output. For instance, if we have two neurons here that have a specific value as an output, we run them through a function, and by running them through a function, we modify them. And that and the hidden layers help us to create these new models, which are usually referred to as nonlinear. So these are nonlinear, and these are over here linear. Okay? So basically, here we will use all the code we have developed so far. That's what's so great about this, is that by learning linear regression, we were actually doing several things, learning about models, learning about linear regression itself, but in particular, learning about TensorFlow and learning how all that code can now be reused. So the only difference is that now we will redefine some of the code. So if you remember, I had mentioned that in particular, we created 4 core functions, but 2 of them have to be changed now. Whereas before, inference looked like, that, and loss function looked like, right, like that. These are now going to be changed to be more specific to logistic regression. And that's what's so great about it. All we have to do is worry about the contents of those 2 functions. But everything else pretty much stays the same. As we can see in the next code segment, inference is mainly different from the linear regression. So we will see this in the inference function, in the linear regression approach, because we now run our equation, this equation, through a function, which is called the, let's say the softmax or sigmoid. So I'm just going to say S, and so now this is plugged in here, so that the output is, whereas this one, let's say, was Y, this is now, Y star. So something else, right? So we create a new function by mapping the output of this equation through a function, and that's called an activation function. So these are called activation functions, and this is a key component of machine learning. So as we can see in the next code segment, inference, the inference function, right? So inference is mainly different from the linear regression approach because we now run our equation, our very famous MapMol equation, which, remember, again, takes x and w plus the bias, right? And we run it through an activation function. So we run it through a softmax function in particular. Softmax function. Okay? So additionally, instead of predicting a real valued number, remember we're no longer predicting housing prices, with just one output neuron, we now have several output neurons, which represent each possible class. So, for Iris it would be 3, and for MNIST it would be 10. So intuitively, think of it this way. So I will provide an example of this. All right. So let's imagine this example. So we're going to take our housing price example again. All right. So we take housing price. So for the linear regression problem, if you remember, we were predicting housing prices given square footage as such. So we had housing price here. We had housing price, right? And then we had to learn a weight, right? To learn the contribution of square footage plus the bias. So this translates into this equation. So y equal W1 times X1 plus B. Okay, so that's our equation. So this formula, if you want to plug in some values, we could make it look like this. So for instance, here we assume that we calculated a bias of 500. X1 is 5,000 square feet, so square feet. And then we also learned that the weight is, let's say, 50. This is just some made-up equation. But this equation would give us a value of 250,500. So this is linear regression. Okay? That's what that is. Now, the model, and there's a little error here. This should be 50. Not 500. So let me scratch that out. So in the model learned in the previous equation that 50 was W1 and then 500 was the bias with an input of, say, 5,000 square feet. And given that, it can predict a housing price. So if you remember, this is a network of one input neuron, right? The 5,000 square feet, right? So the input is 5,000 square feet, and then the output was 250,500. Okay? So, but the question is, how can we represent a model of several classes, right? So we're saying that linear regression and logistic regression are similar, but how can we represent, how can we just add that, right? Or maybe another one over here. So how can we do that? Well, from a graphical point of view, you would just think, well, if I had one connection, why not do that? Right now I have 3 connections. So now, intuitively, this meant 250,000, so this might mean, say, 150,500, and then maybe this one means 350,500. Is that possible? Okay, those are numbers. They're not necessarily classes, but what if these are the only prices that are available? Okay, so then basically this becomes simpler. It just means, low price, medium price, high price, right? So think of it, right? So, this basically tells you that numbers, yeah, you can have a real valued set of numbers, but also there's interpretation, right? Why not just say low, medium, and high, right? And the machinery here maybe can account for that. Maybe the model, if we just tweak it a little, if we think about it a little bit, we can modify it in such a way. So if you think about it, whereas we were predicting one housing price with one input, now we can predict maybe 3, but the 3 actually have a different meaning because not all the prices are common. And so actually we start to reduce our space of outputs to just 3. And so it starts to become more of a class problem than a regression problem. So the question is, how can we represent a model of several classes, such as a model of the Iris data set, which has 3 classes? All right, so let's think about what we know, right? Let's think about what we know as we make this transition. We know in linear regression, we can learn to predict real valued numbers given inputs, right? Again, we have our little graphical model there. From math, now there's another thing here. So we're kind of just taking the things that we know. From maths, what do we know? We also know that we can run real valued numbers through certain functions to obtain scaled versions of those numbers. We have already done this in the videos, right? Whenever we had x and we ran it to the scalar, right, we would get x normalized, right? X normalized. So we've already actually done that. We know that we can plug in a value through a function and get another value. It turns out that in, as we know in maths, there's a lot of those functions that are available, right? Log, natural logarithm, these kinds of functions, sigmoid, tangent, and all kinds of functions like that. And so that might be, what we're going to do, right? So sine, cosine, all of these. So for maths, we also know that we can run real valued numbers through certain functions to obtain scaled versions of those numbers. In this case, a function such as a sigmoid, or in particular for our case, what is called a softmax, can do the following. Right, so look here. We had our original y. We run it through a sigmoid or softmax function, and then the output of this is a new y, right? So a modified version of that original. So this, of course, assumes that this y is this one. So that's just our model. So given our input x times w plus b, we get y that gives us some value. We plug that through the activation function, right? So the activation function, such as a sigmoid softmax, and then that gives us a new value. All right, so that's something that we know already, right? So we can call that, our activation functions. Or some modifying function. All right, so we know that. So now let's look at the example further. So again, let's say we're looking at the softmax here. So some function for now. Let's just think of it that way, right? So we have our little function here, like that. All right, so this function will take any value, right, and convert it to a value in the range 0 to 1. So that's basically the definition of our function here, sigmoid type of a function. All right, so we take any value and convert it into a value in the range from 0 to 1. So we're assuming we have something like that, right? So any value that is x will be converted into a value, between 0 and 1. So something like that. Right, so the mapping function can only be from here to here, for instance, so from 0 to 1. Right, and then over here also, right, from 0 to 1. So given any x, it's always going to be either a very low 0, so we could look at this, kind of like that as well, right? So x is 0 over here, this is 0, this is a high, and then, it goes over here. So it falls within that range. So, that's kind of the intuition that we're looking for here. So this function will take any value and convert it into a value of a range between 0 and 1. And that's just our definition. So for example now, given our previous equation, right, y equal w times x plus b, which is this one, we plug in all the values. We put in the square footage, which is this one, the weight, 50, the bias, which is 500, right? And that gives us 250,500. We run it through the function s, and now we have a new y. Given this definition that it is from 0 to 1, we end up with 0.80, right? Just some example. This may not be, like I'm just making up numbers here, so the calculation may or may not be the actual number, but this function provides the conversion, the mapping, if you will. All right. So that's something we already know. So this allows us to learn. So now that we know this, we know that this allows us to learn functions that predict values between 0 and 1. This is good, though. If we think of the intuition of this and the interpretation of it, this is good because these values can also be interpreted as probabilities, right? So you can start to think, if you saw the value is 0.80, all right, between 0 and 1. Whenever we think of probabilities, we think of that, right? What is the likelihood that this is between 0 and 1? So this is good because these values can also be interpreted as probabilities or strengths of my prediction, right? So as in, I have these are not, in the strictest sense, they're not probabilities, but I'm just saying they can be interpreted as that. So as in, I have 0.80 confidence that the housing price will be $250,500. All right, so now knowing this, let's think a little bit more about this. So what if I had 3 possible housing prices, which is what I said, right? So I have now 150, 250, and 350. So I have the low, the medium, and the high, right? That's really what that means, We all think of that, and whenever you're trying to buy a house, right? So can I buy a medium price house or low end house price or a high end house price, right? So or price, price for a house. So how can I represent this in the previous equation? So that's really the key thing. So now we have this idea of mapping these 3 prices in some other way, right? So how could we do that? So for this, we built one equation for 250, right? That we knew. We could build one equation. So what about, we can probably or definitely learn equations for the other 2 prices, right? So we could do something like this. So if you look at it, here's the pricing, right? Here is a weight for these, a different weight, right? Given it's a different equation. The x is still the same because this is square footage, right? And then, but we have other parameters in place here, and then different biases, etc. So with this approach, we can, possibly learn these equations, right? So if you think about it, whereas before we had 1 equation, we have now 3 equations. Now, intuitively also, think of the network. If one network looked like this, now because we have 3, we have 3 separate networks, 3 separate linear networks. What do we know about these networks? Well, before the network was given x1 and given the y output 1, right, we would have this. But we know that x is actually, there's only one x, this one, and this one, and this one. So it's the same. So actually, this x does not change for the 3. We do learn the w's, these, right? So that's going to be w1, w2, w3. And we have different outputs, right? So that's going to be then y1, y2, y3. So that kind of, we should be able to understand that. So if you think about it, we only need 1x here if we want to graph this more economically. So these 3 become 1, and then these 3 are still separate ones. So now we could just do this, right? And if you see now, we've built our first network just by doing that. So now if you notice, we have created a system of 3 equations. We have y1, y2, y3, which is the output, w1, w2, w3, which is the weight, b1, b2, b3, and x is the same for all of them. If you look at this as a network, you can see that it has 3 output neurons and 1 input neuron. And in fact, the network will look like this, right? And you can see it here. So the 3 housing price equations architecture. So this is our first architecture that we've built. We have 1 input, which is x here, right? And then we have 3 outputs, and they are y1, y2, y3, and 3 weights, w1, w2, w3. And then here, remember that this always has plus b1, plus b2, plus b3. So we have this new network that we've created, all right? Whereas before we had 3, right? We can combine them, 3 linear regressions basically. Now we have 3 linear regressions still, but kind of connected in a network. So now there's the other element that we knew. We knew that we can apply a function to a value and convert it into another one, right? So that is, if we apply our sigmoid or softmax function, we can change the value. So that basically, given whatever the function is supposed to do. So in our case, produces values between a range of 0 to 1. So to each equation, then we can get, given this was y1, w1 times x plus b1, right? So we had that equation. And then now that equation, this value here, y1, right, is plugged into a function, right? So that's this part over here. And so that's going to produce a O1. So we do that for each of the 3 equations. So we have O1, O2, and O3. So notice how we have changed this a little bit. Okay. So now if we go back to our example of housing prices, we have a new set of outputs which are now scaled to be from 0 to 1. So our formulas that looked like this for linear regression, 3 linear regression formulas, now look like this. All right, so can now look like this. All right, so we have the actual equations here, the function, and then it produces a set of values, right, as defined from 0 to 1. So this intuition hopefully shows you how you can train models to predict basically confidence of a specific output neuron, such as confidence that given a square footage of 5,000, the housing price is more likely to be 250,000 based on the 0.7 confidence interval. All right, so that's kind of the intuition of this. And you might be asking yourself, but if it's 5,000 square feet, shouldn't it always be either medium, low? And that's certainly true. What would happen is really that as we learn this, what would happen most likely, given that there's only one input, is that these 2 values would be very low. So they would be 0.002, this one might be 0.001, and then this one is like 0.70 or something like that. Notice here that they don't necessarily, although they conveniently add it to 1 here, that's not, so far we don't have the machinery to do that, right? So this value could be like this, and these don't add up to, they don't add up to 1, because we haven't done that yet. So we have a problem. That's one problem that we have. And the other issue that you might say, well, this doesn't work because if it's 5,000 square feet, it shouldn't sometimes be low or sometimes be high and sometimes be medium. And that's true. And that's why I think what would happen is that actually the values would always be like this and then like this. If you notice, this value tends to 0 and this value tends to 0. This value, on the other hand, tends to 1. So whenever you have this, you wouldn't, so if you think about it, your output would not be, if you just think in terms of how close is this to 0 or 1, your output would not be 1, 1, 1, right? And you don't want your output to be 1, 1, 1. Instead, you would want your output to be just one of these and the other 0. So in that case, 0, 1, 0, which if you look, it's this one, right? So this one that tends to 0 is this one, and this one that tends to 0 is this one. This one that's 0.70 tends to 1 and is that one. So that's really what you're looking for in a logistic regression. And we can see how we are getting there, but we still have a few problems. Now, how will it learn that it should be medium versus low and high? That's going to come from the training data. So it's just going to come from the fact that whenever you give it 5,000 square feet, guess what? It learns these values. But in particular, you want it to learn something more like that, right? So that's really what you wanted to learn. So it's better then to give it data like this than to give it data like that, all right? However, for us to do all the math and express the inference functions, this is the approach that we want to follow. Okay, so let's stick with this example for now, and we've already identified that we have a small issue here with the 0.7. It doesn't quite add up to 1, so we do have that issue to solve. So, so in summary, this intuition hopefully shows you how you can train models to predict confidence, the confidence of a specific output neuron, such as confidence that given a square footage of 5,000, the housing price is more likely to be 250,000 based on a 0.70 confidence. Finally, to train this model, you do not need to give it the housing prices, right? But just the output neuron associated with the inputs, right? So this is what I was saying. So the 0, 1, and 0. So in this case, our X matrix would consist of one sample, right? So X would be 5,000. And so that's X. Then there might be another, if let's say square footage is 2,000, right? So for the 5,000 square footage, this should be associated with the price 250,500, which we've actually determined to be the medium, right? The medium price, which another way of saying this is the medium is to use a one-hot encoded 010, all right? And then for the low one, so if we gave it 2,000, this would be 150,700, which if you think about it, that's the low one. But really, the way that we want to encode this is 100, right? That would be the low class for one-hot encoded. So finally, to train the model, you do not need to give it the housing prices, but just the output neuron associated with the inputs. So in this case, X matrix would consist of one sample, 5,000, associated with the correct output neurons or output neuron sequence. Now, we did say that we had a little problem with the softmax, right? Or the fact that we had values, you know, we can end up with 0.8, 0.70, 0.59, and these do not add up to 1. They are not equal to 1, right? This is in fact bigger than 1. And so it doesn't quite act like a probability, but when we have the classes, we don't want to end up with 110, right? Because this is 0.80 and this is 0.70 and then maybe this is 0.02. Instead, what we want to do is we want to end up with values that look more like this. You know, if this is 0.80, then maybe this is 0.15, and then this one is 0.05. So this is what we want. So we need to find a way to go from this to this. All right, and as it turns out, there's a function called softmax, all right, and the softmax function can help us to do this. So formally, a softmax function is a way of mapping a vector of real valued numbers in any range into a vector of real valued numbers in the range of 0 to 1. You can see it here. But where, additionally, all the values add up to 1. Right? So that's the critical component that we need, and it turns out we can do it with the softmax. So we just have to add that in to our code. So the result of the softmax therefore gives a probability distribution over several classes. So more formally, we can define the softmax function as follows. So the softmax can be written. You can see here, this is the softmax S. Given an input, a specific value, let's say yi, then it's just going to be yi, it's the exponential here, so e to the yi, right? That's in the numerator, divided by the sum of all the e to the yi's of all the possible classes. So if you have a 3-class problem, right, you know, remember you have y1, y2, y3, So this is equal to saying, the sum, so I'll just do e y1 plus e to the y2 plus e to the y3, and the numerator is just going to be e to the y, let's say 2, which is the one that you're doing. All right, so that's basically what that equation does. We will see another way of doing this with Python. All right, but basically the idea is that by doing the softmax, you end up with the values that add up to 1. So this function takes the y value as inputs, all right, the y values as inputs, which are called actually logit scores, and produces a new vector where all the values add up to 1. So for example, it can take 2, 1, 0.1, right? These do not add up to 1, and maps it to this vector, 0.7, 0.2, 0.1, which does indeed add up to 1. So we can see here in Python, Python code, and run this in your Python environment and see that it works. So basically, the previous example is the logits. So we have 2, 1, 0.1, right? And then we call the NumPy library NP, and then this is a list comprehension, if you remember, right? So we're going to do for I in logit, so that means we grab every single one. So we got 2, 1, 0.1, right? And all we do is we take that I for each iteration, and we use numpy.exponential. So that's e to the whatever I is here, right? So we do that. And so we are just saving these into a list, an array. So now we end up with a list that looks like this. So it's going to be e to the 2, e to the 1, e to the 0.1. Right? So we end up with that here. And then once we have that, if we want to add them, so the denominator part, right? So sum, and now I have it for my denominator part, sum of exponentials. Then I want to create a new vector now, and again, the same thing, a list comprehension. So for j and exponentials, I'm going to iterate through all of these, right? So this one, that one, that one. And then I'm going to create a new vector now of e to the 2 plus the sum. Okay, so I'm just going to write that. And then e to the 1 and the sum. And then e to the 0.1. Right, and that's it. So that gives you a new softmax. So if you print this softmax, it would give you this array. And if you print sum of softmax, it'll give you 1. So it adds up to 1. So that's pretty much what the softmax, so Python softmax, does. Okay. So now that we have that, we are ready. All right. So now we have all the tools that we need, and we are ready to define our TensorFlow code. So if you remember, we had in the previous video talked about linear regression, right? And we looked at the inference function. So the inference function is nothing more than the prediction, right? So it's the prediction of y equal w1 times x plus b, right? So that's what we were doing before. So we define the inference function by doing this, right? So we had something like that and like that. All right, so we needed to create a w, right, which was variable, tf variable. All right, and we made it to be, the w is of dimensions 1 and 1 because, remember, there's only one neuron here and there's only one neuron there, right? So w is 1, 1. Right, so and it's initialized to all zeros at the beginning, right? That's why we have this here. But these are the dimensions. All right, then we define the bias here. The bias is also TF variable of zeros with just size 1 because that value is 1. And finally, we define the equation over here, right? So TF mat mul, remember that's the power of GPUs, right? So matrix multiplication, so we do x times w plus b. All right, so we do all of this, and then that gives us y, and then we just return the letter y. Now that we looked at linear regression, we are ready now to do the simple logistic regression to define the network architecture. So notice that it's basically the same with a few differences, right? So disregard this init for now. I'll explain that. And then if you notice, there's still a W, there's still a bias, right? You can see here that whereas W in linear regression look like this, and bias look like this, now in logistic regression they look like this one and that one. Now nothing has really changed. I mean, we have a few other things in here, but it hasn't really changed. These W and B are the same ones as before, except there's a new function here, but this is more for efficiency than for anything else, and I'll explain what that is. But what I want to stress right now is that inference, let's say the linear regression model from before could have this, could have that, could have this. So that's not any different. If you look at the equation inside, it's still also the same. Mat mul xtf w plus b. That's still the same. The one thing that is new that we didn't have before in our linear regression was, if you notice, we just had tf mat mul x wb, right? That was it. But now, notice, we added this function, tf_nn softmax. And so that basically means that we take the y, and now we are plugging it through our s function, our softmax. And then that becomes the output that we return. You see, so that's really the only difference in our inference function between linear regression and logistic regression. All right, now let's talk about the other things that are different in this function. So let's start with this one. Init tf constant initializer 0. So that basically means, let's say we had two weights, w1, w2, right? If we had two weights, we could initialize this to zeros. We could initialize this to ones. Or we could initialize this to, let's say, 0.5, 0.5. Or we could initialize this to something else. This could be randomly 0.3, 0.03. Right? Whatever we want, we can pick a distribution and initialize it that way. So that's what the tf constant initializer does. It allows you to define what these initialization values could be. So if you notice here, we defined that we want it to be 0. And this object, remember that this is just another node in the computational graph, can be accessed by init. Right? We can access that by init. So that can be an input for something else. So as it turns out, whereas before we were just using tf variable like this for the linear regression, now we have a slightly more powerful function called get variable. Right? Get variable. So get variable is it's what's recommended now by the TensorFlow framework for people to use. It's more efficient. It's got a little bit more computing power. It allows for reusability of the memory buffers in a more efficient way, etc. So the recommendation is basically where you would use variable before, now use get variable. So whereas before we were saying, use variable, now the TensorFlow framework says get variable. It's a little bit more efficient function, allows you to reuse variables, etc. So additionally, notice we can name it, right? So, this is useful because remember, we are building a computational graph, and the computational graph has like a mat mul node, and then this one takes x tf, and then the w that we learn, and other parameters, right? And it takes all of that, says plus bias, etc. So all of this, these are nodes, but sometimes you may want to name the nodes, right? So for instance here, w would have a name, and the name is actually w, right? So that's what that basically does. So this part here allows us to create this node. We reference it with get variable, we give it a name w, we use an initializer, that is this one, right? So basically we initialize all values to 0 here, but the goal is to show that it could be something else. And we specify the dimensions of our environment. So remember that the dimensions here, A and B, are usually going to be the neurons in the previous layer, whatever they are, and the neurons in the next layer, right? So in this case, A. So in this example here, this would be 3 and 3. So in our example, if we were doing iris, this would be 4, and then this would be 3, right? 4 and 3. Right, but for now, we just plug it in as A and B, and that way, later on, this can be defined. If you prefer, you can always hard code this. That's perfectly fine as well. That's just a preference. Bias is the same, so you just get variable. We give it the name B, so you could say B here, right? And then initializer, again, we use the same initializer, so it's initialized to 0. And then here, the dimension, remember, it's only... So bias, always think of it as, adding it to the next layer. So like that, right? And so in this case, if we were doing this, it would be 3 or whatever it is. But these two match, so it's whatever that number is. Right? So by doing this, I like this approach because you can always reuse the code and just really play around with the dimensions of the tensors that you're creating. So those are the differences, so the TF variable and then how we define the parameters and then the initialization. So you can see here in summary, notice that we can use TF get variable instead of TF variable. Here to declare W and B, the values A and B represent the previously defined that we saw in the previous video, so the number of features and the number of classes. Or more generally speaking, the number of neurons in one layer and the number of neurons in the next layer. Because keep in mind, it's features and classes here because we have no hidden layers. But once we have hidden layers, it'll be just, we'll be looking at that segment. And so it's basically better to say the number of neurons in this layer and the number of neurons in the next layer. Now, as far as the difference between TF variable, as I said, and get variable, it has to do with reusing the same variables. Basically, TF variable is older, whereas TF get variable is a newer version and more efficient computationally. And the suggestion in the TensorFlow framework is on this issue is pretty much, from what I've read online, and I've had this question for a while, it's just pretty much forget TF variable and always use TF get variable instead. And so I've seen that it works, and so I use it in that sense. So assuming we are working with iris, A would be equal to 4, B is equal to 3. Right, so we have a network like that. And the drawing below shows the architecture that I just created for a logistic regression problem. Keep in mind, there's no hidden layers. If you look closely, you can conclude that logistic regression model is like a neural network, just without hidden layers. There are only 2 layers, which are the input and the output layer. A hidden layer would be a layer in between input and output that connects these 2 layers, so something that goes in there. But we don't have one of those for logistic regression. However, all we have to, the great thing about this is a neural network is just the same thing as a logistic regression, few modifications, and add another layer. So we can see that here. So this is our logistic regression architecture for the iris data set. So this is x1, x2, x3, x4, and now we have y1, y2, y3 because we have setosa, virginica, versicolor, etc. Now notice that the bias would still be just b1, b2, b3, but the weights have now again exploded. W3, then we have W4, W5, W6, then W7, W8, and so on. Actually, there's so many, right? So it would be, there's maybe another way of doing this is highlighting them. So this one has 1, 2, 3, 4. So each one of these has 4. So this one has 4, 4. So that's a total of 12 weights at this point. Imagine once this becomes more complicated. Let's say if you have 1,000 neurons of input, right, in 10 classes, that's a very big set of weights, right? And that's what makes actually the problem more computationally intensive, because you have to learn those weights. But anyway, this is our model of logistic regression. So for the previous code segment that we saw, in W we can see that we create a matrix A and B of size 4 and 3, right? So again, because we need to have a, it's 4 and 3 because it's really a matrix, right? It's like you're saying x1, x2, x3, x4, and then over here we have w1, w2, w3. So we have to learn this weight, this weight, this weight, this weight. That's the 4 weights for y1. Then this weight, this weight, this weight, this weight. That's the weights for these are the weights for y2, and then this weight, this weight, this weight, which are the weights for w3. So that's the same as looking at these, right? So these over here. The B vector bias has a dimension equal to 3 because it only needs to be added here to the output. So there's only 3 for the output neurons. That is, there is now a bias for every neuron in the output layer. And additionally, as I said, notice that the variable init in init constant initializer helps to initialize TensorFlow variables, as I explained. Now there are other ways of doing that init. As I indicated, it doesn't always have to be zeros. Instead, it could be a normal distribution. Etc. And we will see that in the future, videos. Similarly, the loss function. So now, we looked at, remember, we looked at inference, and we looked at loss. Right? So we already covered this function. Now we're going to focus on loss. So if you remember in linear regression, this is the function for the least squared errors, right? So we had y minus y hat squared, right? So now in logistic regression, this is a bit more complex, and so we have to change it because it's a different logic. So similarly, the loss function is also changed from the linear regression version. In the linear regression version, we used LSE, least squared errors, loss function. In this case, we now use a logistic regression cost function as shown below. So you can see that here. All right, this logistic regression, so this is the loss function. Right, so this is the loss function. So logistic regression uses a cost function, so let's be consistent with the word, cost function, called cross entropy. And you can see that here. So basically the idea is that you have a cost, right, and you are comparing, again, y hat to y. Y hat to y. So what is y hat in this case? Y hat is nothing more than the prediction equation. So it's going to be our weights times x plus b. That's this part here, right? The T here just stands for transpose. So this is just a linear algebra thing. Whenever you're multiplying a matrix times a vector, don't worry about that for now. But really, just want to show that this is what we've all been doing, right? W times x plus b. That's this part here. But then, because this is logistic regression, we talked about how this needs to go through a mapping function, right? So that's the G. Think of it as our softmax function from before. All right, so this is the cost function that we want to calculate, and this cost function is actually defined as this. It's sort of an if statement. So we're saying, remember that this is a classification problem. So we have no real values anymore, but just two options. Whether, y is either a 1 or a 0. All right, that's our cost function. So basically what we're saying is, if y is 1, we are going to use this function, the negative logarithm of, the sigmoid function mapping as its input the y prediction function. On the other hand, if y is 0, the other class, because remember that we already said that for logistic regression, the sigmoid is mapping to values in the range of 0 to 1, right? So you remember that that's one of the first things we said. It's being mapped to 0 and 1, and so we really just have these. However, we really want, our objective is for values to be either 0 or 1, not really even values within 0 and 1. Right, and it so happens that the machinery here helps us to do that, because our inputs are not going to be, we would have a problem if our inputs were 0.7, 0.3, 0.0, but our inputs are not going to be like that. In fact, our inputs will always be 1, 0, 0. Right, so it will always be the actual value. So then we have the classes. If the input is y equal 1, then we use this loss function. If the input is y equals 0, then we use this input. Minus log, and then its input is 1 minus the function here. So another way of writing that, in the previous code section, the G, represented the sigmoid function or the softmax, right? So we can also write these equations as follows, right? So instead of doing the y, we usually just do h0 x, where this is wx plus b g, right? So that's another way that we can write that. Okay, so the exact same equation that we had there, right? We are just now, so this equation, right, is being replaced by this equation. Okay? Now, so what does this represent? So what do you capture here graphically? Remember that these functions represent optimizations, right? So they represent some kind of a cost function. So they have, if you have a quadratic function, whenever we, have a quadratic function for the loss function, it looks something like that. Other functions might be kind of like that, right? In our case, the logistic regression as a loss function has a specific graph, right? It has a specific graph. So for instance here, we can see that in the next slide. Remember, we have two scenarios, right? So we can see the two scenarios here, all right? So the scenario of 1, we use this one, and then whenever we have the scenario of 0, we use this one, right? So 1 minus there. All right, so these are the two functions, the if statement, right? And this is what we want to optimize. Now, keep in mind, this is not the data itself, right? So the data, x's, zeros, zeros, that's one function, right? That you're trying to learn this line to separate the classes with a logistic regression classifier. But that's the inference. Because remember, again, inference is y equal mx plus b. mx plus b, we learn, is a function for a line where m is the slope, right? Or that we can rewrite as w. So that's one space, one graphical space. But then the inference function is that the loss function is now another function, right? So before we had LSC, right? So sum of y hat minus y squared, right? That's what we had, right? We know that quadratic functions have a shape, if there's a law a loss function, they look something like that, right? In our case, we have the logistic function, okay? So the logistic regression looks like that. That's its graph. So they represent these shapes, basically, which I had drawn already, right? If you remember, when I talked about the sigmoid, right, I said that it had to be between 0 and 1. So these equations here represent those shapes, but there's two of them now, right? So what we have to do is we have to say, well, if the classes are 0, then we're going to optimize for this. If the classes are 1, we're going to optimize for this. And that's what we see here, right? So we see here in these graphs. So how do you interpret these graphs? Basically, the objective, because remember, these are loss functions, logistic regression, let's say optimization. So what we want to do here is we want to optimize something. So let's say that the class, the real class, the actual real class is 1. Right? So what is the objective of the function then? You notice that this Cartesian plane here is a cost function versus the predicted. Remember that this is h0x is y hat, right? And this is y real. So it's the predicted versus the actual. All right, so what is the objective between these two? Just like in linear regression, right, where you had, y hat, the predicted versus the real. Here we still have the real versus the predicted, except that we have them in a different kind of loss function, right? So this is cost here, and this is the predicted, so y hat, let's say. So what is the objective here? Well, the objective is if the actual value is 1, then we want on this axis, the x-axis, right, on this axis, we want a mapping of the predicted to the cost. So we want basically that the cost is very low, right, when the predicted value y hat tends to 1. Do you see that? So it tends to 1. So the closer it gets to 1, from 0 to 1, right, the closer, the lower the cost. So that's what this function represents, is that, if this is, the real is 1, but our value is closer to 0, then what happens to the cost? The cost is really high, right? So the cost over here is, whatever that is, really high. So we want to minimize the cost, and this representation, the equation for the loss function, allows us to do that by, penalizing y hat when it tends to have a low value here, which basically means as it gets closer to 1, because this is 1, then it is minimized. So whenever we have a training sample, right, in the model, we give it this sample, y equal 1. The function definition that we have produces, given this y hat, a high value. So what do we do then? We discard those weights. Then, you still know that the training sample was 1, so we pick another set of weights. Those weights go into the new y hat function. It predicts a value. Given the loss function, those values give a low cost here because it tends to 1, and so therefore we optimize it. So those weights are better than the other weights. That's the same here. Now, whenever we have a training sample that is, a real training sample here that is 0, then our objective is now this graph, right? This graph over here. So again, this is y hat. So we want y hat to pick a set of w's, weights, right? If it picks a set of weights, right, that define h0x, then w or y hat predicts a value, right? Given the loss function, if that value tends to 1, it means it's opposite to the 0, right? It's the other part of the range, so the cost is really high. So that set of weights is bad and we don't want it. Instead, we pick another set of weights over here, right? Those weights go into H0, which is the y hat. All right, so y hat now predicts a value closer to 0. Given the loss function defined here, right, a y hat close to 0 would give a low cost, right? The cost is just very small, and so that's a good one that we want. So that's how we know, okay, those are the parameters that we want. Because the cost is low, it tends to 0, the real value is 0, and so we've met the objective, okay? And so that's the loss function of logistic regression. So this is the loss function. All right, now that we've defined that, for convenience, what practitioners do is they will combine. So where we had the if statement here, if use 1, or if y is 1, then use 1. If y is 0, use another one. Now we can combine them, and if you notice, this is really the same. We just have both functions in the same equation. So for instance here, if y is 1, right, then that means we plug 1 here, so this is 1, and so this remains. 1 times that is that. But here, 1 minus 1 is 0, so this term just cancels out. You see that? Cancels out. All right, and so that's equivalent to saying y is 1, we want to use this function here. Now, on the other hand, if y is 0, then it means it's this one, so we want this function. So this is 0. That means this whole term becomes 0. This is 0 here, so this becomes 1. And so we end up with this term, which is actually that term over there. And so we have a way of choosing the optimization. Okay? So that's a convenient way of writing these equations. So now you can see it here again. So for convenience, in the previous logistic regression functions, the previous functions can be written as the following function, which I just explained. So now that we have all of that intuition, we are done with the theory of logistic regression, and now we are just ready to write the code, right? So remember, so this is more related to the code. We have to define now inference, and we've defined actually already inference, and now we just have to define loss. And once we do that, we are ready, all right? So now in inference we define the architecture. So in inference we define the architecture. In loss now, we are going to define, the cost function. All right, so the following code in the next slide shows the implementation of the loss function for logistic regression, as if we were writing out the equations, basically. Now, I should say one thing. This will, I've tried to write the actual equations that we see in the math for both linear regression and logistic regression, just because, to kind of see how it goes from theory to practice. However, going forward, I will not actually write the equations as they appear in the math, and instead we will use the built-in TensorFlow functions. Now the built-in TensorFlow functions, allow us to, instead of writing a whole bunch of lines of code with equations and having a few problems, we can just use the efficient ways in which TensorFlow has defined for all the different models. So there's all the loss functions are already defined in the TensorFlow framework with just one function call. So it makes it a lot more practical. So, but anyway, in the next example, we will see the loss function for logistic regression as if we were writing it out, as if we were writing the math equations, basically. One important thing to mention, though, is that this is not always the best approach. It creates problems. It's not numerically efficient. It's a numerical method, basically, of approximations. And so you're going to have problems. And so because of that here, we will need to add, for instance, this little function before. All right, so it's called a TF clip by value. So this little function will be to kind of like tweak a little error that otherwise results when we're using the non-built-in functions, right? So if we code the equations ourselves. So, basically be aware that you can do this, but the recommended practice is really to use the built-in TensorFlow loss functions, etc. So, why do we add this? So I noticed when running this code, I've noticed that this model does not always converge, basically. So to correct this, we've added this line of code. You can see this here, and you'll see it in the context. But basically what it does is it takes output and it creates output 2. So it needs to clip something in the data, all right? And we'll see that in a second. So the clipping function, this clipping function, so this line of code helps because some values in the process become not a number. And you don't want that, right, when you're doing a lot of computations. And the clipping in the function basically addresses this problem. So this approach of writing out the cost functions, as I said, is not always the most optimal because of these reasons. All right, it's not always the most optimal. But I have shown it here, for contrast between linear regression and logistic regression. And that's really the only reason. It's definitely, for, with a lot of data, this would be slower than TensorFlow built-in functions as well. So a better approach is to use TensorFlow built-in cost functions for cross-entropy calculation. So they have a cross-entropy built-in function. And in the future, right after logistic regression, from now on, we will always use actually the built-in functions. So future code for deep neural networks will abstract the math part, basically, of the loss function by using the built-in functions. So here we have, this was the loss function for linear regression. If you remember, the very intuitive, y hat minus y square, the sum, so there's pow and sum and everything. So really nice. This is a very satisfying code where you can go from the math to the actual code in Python. Right, and we already explained this in a previous video. I added this here just to show the contrast. Notice that it's still loss, still the real versus the predicted value here, right? And now we can look, from this one, now we can compare to the new one. All right, and we can see here that for the logistic regression, the loss function still loss, still output, so the real versus the predicted, right? That's still the same. The names may have changed, but it's still the same thing. We still return loss, but now we have all of that code. Notice how from one line of code we had to go to 4 lines of code, right? And so this is not always the best practice. So in the future, use built-in TensorFlow functions. But I'll explain this. So if you notice, here is our TF log of output. So that's basically, when we did log, and then we did H0, right, X. Except that output we know is actually output 2 is actually, through the clip, output, regular output, and we know that output is actually our y hat, right, which means this is x times w plus b, but also that it goes through that softmax from the previous code, right? So we know all of this. So we'll see how, everything connects here in the graph. This is the information. It goes through that softmax function. That's our y hat. We call it output. We clip it, and so on, and that goes in there. And this was the loss function that we just saw. So you can see that that loss function is reflected here. If you notice, this is actually, and then we have this times the actual real value. If you notice, this is actually a simplified version of the previous equation. So this is actually a simplified version of this one, right? So whereas here we have, in the math we have here, as it turns out, machine learning practitioners, have determined that you can simplify the equation even further, and you just really need to optimize a specific aspect of it, and that's enough. So I'm not really going to go into all the details of this transition, because ultimately we are not even going to use this approach. Instead, this is more of a math approach. Instead, we want to use built-in functions. All right, built-in functions. But I use this example actually to motivate why you should use the built-in functions, right? So, because there's so much that goes into it, into dealing with numerical issues like not a number, right? You have that. But if you use a built-in function, that already, imagine it already has that clip in there, that clipping by value function that does things more efficiently. Additionally, it turns out that you can always modify the computation of an optimization, so the math equation is simplified even further. If we try to minimize the other function, this other function, it turns out it's going to take longer. It's going to be more complex. It might cause more errors, and it's not necessarily going to give you a better result. So it's been simplified by doing this. But again, a lot of work had to go into figuring this out. If we use the built-in functions, we don't have to worry about that. All right, and then there's a lot of other steps here. So we get the dot product. Now here, notice we have reduce sum. This is a new function that we're using. And then after we do reduce sum, we do reduce mean of entropy, which is, we've already seen how reduce mean works. All right, but you can see it adds a lot of complexity. And so as I said, my recommendation here is to use built-in functions. For logistic regression, I've only done this to show the maths and how it can go from the math to the code. But in the future, once in the next example where we do a neural net, we will see, and when I do the actual lab in the for the code, we'll see how to use the built-in functions for logistic regression as well. All right, so once we have this, so we need to talk a little bit about reduce sum. So let's go here. This is the reduce sum function in TensorFlow, one of those useful built-in TensorFlow functions. Remember, this is in the appendix of the book. I think it's appendix B, actually, in the book. And you can find all of these TensorFlow functions. But here, let's look at reduce sum, an example of how it works. So the function tf reduce sum computes the sum of the elements across the dimensions of a tensor. So for example, here we have a constant 1, 1, 1, 1, 1, 1, right? And so if we do the sum of this, it's going to be 6, right? So for all of it. Now we can also pick that we're going to do reduce sum by an index, either 0 or a 1, right? So if we do this by the 0 axis, it's going to give us the sum of these numbers, right? So that's going to be 2, 2, 2. If we do it on the y dimension, right, it's going to give us, 1 and 1. So that's going to be 3, 3. All right. So that's basically it as far as the loss function, right? So we do we do some mechanical things for things to work. We have the actual loss function. We do the reduction of sum and mean of the values, and then finally loss function is represented here. All right, so now that we've done this part and talked about reduce sum, in summary, what did we learn? We learned about logistic regression. We learned about the theory of logistic regression. So we learned about the theory of logistic regression, and we learned that basically, for logistic regression, we still can use all of the code from linear regression, and we only need to change, really, the inference function and the loss function, right? So we really just need to make those big changes to the code, all right? In a future lab, we will implement linear regression in the code to see how everything fits together, and logistic regression. All right? And this concludes the presentation on logistic regression.